Can you make it a little bigger?
Oh,
yes.
Yeah,
Okay, good.
okay, great. Let's see. Okay. So the title of my talk is Fundamental Limits of Deep Graph Convolutional Networks for Graph Classification. This is actually an amalgamation of several works, partly joint with my co-authors Mayank Baranwal and Al Hero. Partly it's single author work. Okay. So what I'll be talking about is very relevant to the problem of graph classification. What is graph classification? It's the following. You're given a data set of graphs and class labels. So class labels are, for example, either 0 or 1, and then and along with them are graphs. There are many examples of this in chemistry where, for example, the graphs represent molecular structures and the class labels are, for example, is this molecule is it toxic or not? That sort of thing. And the goal is, given this data set, learn a classifier, which is a function from the set of graphs to class labels. And it should be able to predict the class labels coming from the same distribution as your training set.
I have a question.
Yes.
So can you classify whether the graph is generated by one class, let's say preferential attachment, or let's say duplication? This would fall under your model?
Yes. So what you're describing is more hypothesis testing, right? The difference being that in classification you have access to a training set, whereas in the problem you've just stated, you don't have a training set. You just know what the two distributions are. But yes, you have two class conditional distributions, and you're trying to build a function that distinguishes between them. Does that answer your question?
Yes, go ahead.
Okay. Now, typical classification models like neural networks, support vector machines, logistic regression, etc., take vectors in R to the D as inputs. But what we have are graphs. So that necessitates a problem called representation learning, which is you're given a data set and you want to learn what I will call a representing function f that maps graphs to R to the D. So it takes a given graph and it spits out a vector that is supposed to represent that graph in some way. And a representation is good if it helps with the classification task. Now, of course, that's not a mathematical statement. And in particular, what this means depends on what classifier we use at the output. So after you've learned a representation, you take your data set of graphs, you feed every graph into the representing function f, you get an encoding as a vector, and then you have a new data set that consists of vectors and class labels. And then you can apply a classification model such as a feed-forward neural network or a support vector machine, etc. So we are primarily interested here in analyzing a particular graph representation learning method called graph convolutional networks. So how do we evaluate different graph representation learning methods? Well, that's tricky given that there's no one single agreed upon formal definition of them. So the approach that we take is to fix a classification task and study metric properties of graphs that are that basically come from two class conditional distributions. And I want to note that we take a metric approach because a purely information theoretic perspective doesn't tell the full story in graph representation, in representation learning more generally. Why do I say that? Well, one might be tempted to formulate a theory of representation learning that asks, that asks about a given representing function. Can you take the outputs and distinguish between two classes statistically? The problem with that is that information theoretically, it's optimal to simply do something trivial like output the adjacency matrix of every graph, which empirically does not work well, but it doesn't lose any information. Hopefully that's clear. Stop me and ask questions if necessary. Okay, so here's an example of the graph classification pipeline that I worked on with co-authors. The problem was as follows. We are given some complicated molecule, such as the one pictured on the left, and we want to, by some machine learning method, map it to a metabolic pathway class, basically classify it as a carbohydrate, a nucleotide, a metabolite, etc. This is a multi-class classification problem, so it can fit into multiple classes simultaneously. And it turns out that we tried several different classifiers, and the one that worked best, achieving state-of-the-art performance, is the use of graph convolutional networks to learn a representation function for these graphs, the graphs being molecular structures. And then we trained random forest classifier on these output representations, and that achieves the best performance on our test data set. So all of this is to say that graph convolutional networks are widely used, and we ourselves have seen that they work extremely well. So what we'd like to do is understand their fundamental limits. Okay. So as I said, there are lots of graph representation learning methods, but we want to focus on this one, and how we're going to do that is to focus on the performance of this representation learning method on a downstream task. In particular, distinguishing between two different graph distributions. And we'll also study the ability of a given representation learning method to capture different metric, topological, and vector space structures. Okay. So at a high level, here's what we're going to do. We are going to consider the following classification problem. So we're going to fix a representation, which is, so it's a function mapping from graphs to distributions, from graphs to vectors. And we will consider two unknown distributions, D0 and D1, supported on graphs. So you think of these as the two class conditional distributions. So we're going to flip a coin with bias 1/2, and then we're going to generate a sample graph on n vertices from the chosen distribution, D, capital B, comma n. So capital B here is the class label. And then the task for us is, from the vector representing that graph, infer which class it came from with high probability. And we are also going to study metric properties. In particular, we're going to study the behavior of so well-separated graphs in terms of some graph distance, versus how well separated they are in the what's called the embedding space. The embedding space is the set of vectors to which the representation to which the representing function maps. Okay. So is this problem clear? Any questions so far?
Yes, I do
Okay.
have a question. Okay.
Okay, good.
So I understand your formulation is not what happened in real life, but you need this theoretical formulation to actually find fundamental limits, correct?
Well, yeah. So you can think of this as a way of studying the fundamental limits of these objects for graph classification. Specifically, we're asking let's say an approximation question. Do there exist graph convolutional networks that distinguish between two given distributions?
Great question. Thank you.
Yeah, so we are not asking about training questions, which are, I mean, of course, training is important, but that's not what we're asking about. This is more akin to questions of like universal approximation theorems that are studied in the context of neural networks. There, the question is, does there exist a neural network that is close to a given function in a given metric? Okay. Right. So now what I'm going to do now is state more formally what a graph convolutional network is, because these are the main representation learning methods that I'm going to talk about. So a graph convolutional network, abbreviated GCN, has the following parameters. We have a what I'll call a convolution matrix that is derived from the graph G. It's square, and typically it's something like the random walk matrix of G, that is the normalized adjacency matrix of G. It's also sometimes the normalized Laplacian, etc. For us, we're mainly going to focus on the normalized adjacency matrix. Let's see, it has L+1 weight matrices. D is the, by the way, a fixed number. It's the embedding dimension. So it has, so each of these weight matrices is, well, the collection of weight matrices is the set of parameters of the GCN. These are the things that get trained. I should say that in this talk, I'm considering the case where D is fixed, but in the paper on which all of this is based, D can be arbitrary, and I spell out in detail the impact of D on the results. So by arbitrary, I mean that D can vary from layer to layer. So each weight matrix corresponds to a given layer of a graph convolutional network. Okay, then we also have an initial embedding matrix. What is this thing? It is an n by d matrix where each row you think of as a node feature vector. So each row corresponds to a given node. There are, of course, n nodes, and each node gets a feature vector. Finally, there's a choice of activation function, sigma. This is a nonlinearity, as you would see in a feed-forward neural network. Typically, these are things like the ReLU activation function, tanh, sigmoid, etc. As I said, weight matrices are the things that are typically trained from data, but we're asking existence questions. Do there exist weight matrices that have certain, ability to distinguish between two distributions on graphs? Finally, how are these weight matrices all connected up? You start with the initial embedding matrix. You multiply it on the left by the convolution matrix. Basically what this does is for every node, it replaces that node's feature vector with the average of the feature vectors of its neighbors. So it's a neighborhood averaging thing. It kind of smooths out the signal. And then on the right, we multiply by a weight matrix. What this does is for every node, it replaces features with linear combinations of more basic features in the previous layer. And then finally, your output is an embedding matrix. So you have one row for every node. And to get a vector that represents the entire graph, we simply take the average of all of these row vectors. And then that we call the representation of the graph. Hopefully the architecture here is clear. Basically, it differs from a feed-forward neural network in that the structure of every layer is determined by the input graph. Okay. All right. So what is our canonical downstream task? We're going to distinguish between two arbitrary, and I'll qualify this soon, between two arbitrary random graph models based on a sample graph. And we'll ask a few questions. Does there exist a GCN that can distinguish between two given graph distributions or two arbitrary graph distributions? For this, we need a convenient parameterization of a class of graph distributions for this. We can also ask training questions, which I won't really get into in this talk. But the problem is, given a bunch of samples from two different unknown distributions with labels, can we algorithmically construct a GCN that distinguishes between them? And then finally, what roles do the hyperparameters of the architecture play in its classification ability? So the hyperparameters are the embedding dimensions, number of layers, number of neurons per layer, and then the initial embedding matrices. Okay, so what are the random graph models that we're going to distinguish? They're based on graphons. So a graphon is the basic object of the theory of dense graph limits. Formally, a graphon, you can think of a graphon informally as the adjacency matrix of an infinitely large graph. At a bird's eye view, that's kind of what it is. So a graphon, more formally, is a symmetric Lebesgue measurable function W that maps from the unit square to the unit interval. So you take some point on the unit square, you map it to the interval 0, 1, and that gives an edge density. I'll give examples soon. And then we consider graphons to be equivalent to one another up to measure preserving bijections of the unit interval. Basically, what this means is that the graph labels don't matter. It's only the structure. And there's a classical theorem called the Aldous-Hoover theorem that says that graphons are the parameterizations of the space of infinite exchangeable random graph models. Exchangeable here means exactly what I was saying. You can permute the nodes and you get the same distribution on graphs. Okay. So the space of graphons maps, well, if you take them equivalent up to measure preserving bijections, that space of graphons maps bijectively to exchangeable random graph models. So every graphon gives you a random graph model. And if it's exchangeable, the association goes the other way as well. So from a graphon, how do you get a random graph model? Here's how you generate a random graph. You fix a number n, which is the number of vertices. You draw n numbers, which we call latent positions, from the uniform distribution on the unit interval. And then, so you think of these as latent positions of vertices. And then independently, for each pair of indices in the numbers 1 to n, you put an edge between vertex I and vertex j with probability given by the value of the graphon at xi, xj. Okay, so that gives us a random graph model. And I'll give some examples. So one example, so here are two graphons. One is a stochastic block model where you have two blocks. This block here, hopefully you can see my mouse cursor, is denser than this other block here. And we basically, no, sorry, these two blocks are actually, they correspond to edges between classes in the edges between communities in the stochastic block model. And these two blocks here correspond to edges within blocks, within communities. Okay, and you can think of these as having uniform value, let's say P1, P2, and then P3 here. The Erdős-Rényi model is also can also be written as a graphon. In particular, the Erdős-Rényi model is a constant graphon. So the value of the graphon at every point in the unit square is P, where P is the edge probability. Where it gets interesting is you can come up with an infinite variety of other graph models, for example, where you have continuously varying values in this graphon. So it doesn't it's substantially more general than stochastic block models or Erdős-Rényi models. Any questions on the class of models? Okay. So in order to state the results, we need to talk about let's see, we need to talk about some more about graphons. There is a canonical metric or a canonical norm on graphons, and that norm induces a metric. Basically, it's a way of measuring the distance between two graphs. And that also gives us a way of measuring the distance between two graphons. At a high level, let's see. Okay, so we start with the cut norm. What is this? This gives us, so we're maximizing overall subsets S comma T of the unit interval. And what is this thing? It is essentially, you can think of it as the density of edges between these two subsets, S and T. So the cut norm gives essentially the maximum edge density between any two subsets of vertices, where vertices are points in the unit interval. Okay, and that induces the cut distance on graphons. What is this? So this infimum is taken overall measure preserving bijections of the unit interval. Basically, it's saying first reorder all vertices so that the two graphs match as closely as possible, and then you measure. Then you take the difference between the two graphons, and then you take the cut norm of the resulting graphon. And what this is essentially measuring the if you take any pair of subsets of vertices, it's the maximum difference between the edge densities between those two subsets of vertices in the two graphons. Okay, and that's why it's called the cut distance. It's measuring the some sort of difference between the structures of two cuts in the two random graph models. Okay, and that will be our notion of distance between graphs and also distance between graph models. We think of graph models that have small cut distance as being close to each other. Okay, let's see. I just want to quickly give some notion of the prior work in the areas of graph representation learning and the theory of graphons. GCNs have by now a fairly long history. They were introduced at least by 2017, possibly earlier, and they've been studied empirically and to some extent rigorously by various authors. Properties dealing with the generalization and stability for particular loss functions and classifiers were studied before. In our case, we're not restricting to particular classifiers. Let's see. There's also been more theoretical work that connects GCNs to Weisfeiler-Lehmann algorithms. So the Weisfeiler-Lehmann algorithm is it's used in graph isomorphism testing, graph isomorphism and automorphism computations. And it turns out that there is a connection. However, these works kind of ignore metric properties in the sense that they don't really say, so basically they say that for a certain set of graphs, there's a GCN that can map distinct graphs to distinct embedding vectors. We want to go further in this work by asking the following question. So I introduced a metric on graphs. So if I take two graphs that are well separated in terms of the cut distance, does that imply that the embedding vectors of the graphs are well separated? And it turns out that no, that is not always the case, which is a downside of certain GCN architectures, in fact. So that's the key crucial difference in our approaches. I think both have merit, but neither one gives a complete picture of GCNs. On the graphon side, there has been extensive work on the theory of graphons dealing with, for example, estimation. So they ask the following question: given a sample graph from a graphon, a large enough sample graph, how can you estimate the graphon from which it was drawn? Okay, so that's an interesting problem that was studied by various people. Okay, back to our setting. So we're talking about this hypothesis testing setting. We fix two graphons, W0 and W1. These are our random graph models that we want to distinguish between. We fix a sequence of weight matrices, an embedding dimension, etc. So fix all of our parameters of a GCN. We draw a random graph from either W0 or W1, and our goal will be to infer which one it was from. So how are we going to do this? We're going to study the embedding vectors. So we have fixed a GCN. We're going to produce an embedding vector, and then we're going to see how close together the embedding vectors coming from W0 are, and how close they are to those of W1. Okay, so you have two classes corresponding to two random graph models, and you want to, and you draw graphs from these models. You compute their embedding vectors according to one particular GCN, and then you ask the question, how far apart are the embedding vectors? We will furthermore ask the following question, which allows us to study things information theoretically. We're going to assume that there's some noise in the output. So after computation of these embedding vectors, let's say there's, for example, floating point error that produces a noisy version of the embedding vector. And here I'll talk about basically taking the embedding vector and then uniformly perturbing the entries of the embedding vector where the noise is sampled from the unit interval, from the uniform distribution on the interval negative epsilon resolution to positive epsilon resolution. So this epsilon is something that we fix. And then the goal is from the embedding vector, either the noisy version or the non-noisy version, try to infer which random graph produced which model produced the random graph with high probability. And so many of the results that I'll talk about will be from the following paper, which was recently published in the IT Transactions. Okay. Is the setup clear? Okay. So I'm going to dive into the main results. I'm going to start with some convergence results. It's going to turn out that for a there's a certain class of pairs of graphons, pairs of random graph models, in other words, that produce embedding vectors that all cluster around the same point, so that it's metrically speaking, it's hard to distinguish between these pairs of graphons, and we're actually able to precisely characterize when that happens. To do so, I'm going to define the delta exceptional set of graphon pairs. Okay, where delta is a number that so it's you should think of delta as a small number, less than 1, close to 0. So first I'm going to define the degree function of a graphon. So this is a function that maps an x in the unit interval to a number. It's going to be the expected degree of a vertex whose latent position is x. And this is given by the integral. Basically, it's you look at a graphon, you integrate along one particular sort of line segment of the graphon or row of the graphon, and then that gives you the expected degree. The total degree function is the integral along the entire graphon, well, the integral over the entire unit square of the entire graphon. And this measures the expected sum of degrees of a sample graph. That's what it is. I'm being a little bit sloppy here because, of course, that expected number, that number should depend on n. So it's a normalized expectation. And then I'm going to define two graphons, W0 and W1, to be delta exceptional if the following integral is less than or equal to delta. Basically, what this measures is you can think of this as integrating over the so it's an integral of the difference between the two degree sequences of the two graphons. So you can approximate this by taking sample graphs from W0 and W1, computing their degree sequences, normalizing by the number of vertices in each, or sorry, the number of edges in each. So these are two probability distributions, and then taking their component-wise differences and summing up. And then, so this is a difference between degree sequences, essentially. So two graphons are delta exceptional if the degree sequences of the graphs that they produce are within delta of each other in this formal sense. Okay. And we say that two graphons are delta separated if they're not delta exceptional. It turns out that delta exceptionality is the key property that determines whether or not the embedding vectors of two graphons are close together or far apart. Okay, so we come into our first main result. If you have two delta exceptional graphons with delta greater than 0, so in other words, they are within delta of each other, it turns out that in any coupling of the random graph samples from these two graphons, if you reorder the vertices appropriately under some technical conditions, the output embedding vectors of these two sample graphs for any GCN will be within this will be within essentially delta over n of the L infinity in terms of the L infinity norm. So it should be noted, let's see, the entries of these output embedding vectors are usually theta of 1 over n. So bear that in mind. Now this is provided that we're studying GCNs of moderate depth. So this is provided that the number of layers is at least some d log n for some large enough constant d. Okay, so this is saying that delta exceptionality leads to embedding vectors that are close together. And then if delta is equal to 0, that is to say, if the degree sequences of the two graphons are the same up to some set of measure 0, then their embedding vectors are extremely close together. Remember the entries of the embedding vectors are theta of 1 over n, but the distance between them is even smaller. The distance between them is big O of n to the negative 3/2. So these embedding vectors are extremely close together if their degree sequences are indistinguishable. Why is this interesting? Well, it's interesting because, well, it's interesting for various reasons. It's a negative result. Basically, this says that if the degree sequences of two graphons are very close together, then they are hard to distinguish. We have a theorem that says this when we perturb the output embedding vectors by some noise, one cannot distinguish between the two graphons with probability tending to 1. So we have a probability of error lower bound. This is kind of remarkable because the degree sequence is it's of course not it's not the only feature of a graph that we find interesting, right? So if you have a set of representations that that can only distinguish between two random graph models if they have different degree sequences, then that's a negative result. Okay. we also have a probability of error upper bound when two graphons are delta separated. So delta separated means that the degree sequences of the two graphons are one can think of them as far apart in the sense of being delta separated. Then it turns out that an extremely trivial GCN is able to generate embedding vectors that are far apart. In particular, you take the identity GCN. What this is the GCN that takes that takes the initial embedding matrix of each graph and just spits it back out. It performs no transformation. It averages the rows. And it turns out that this generates well-separated embedding vectors between the two random graph models. And so we are able to distinguish between them trivially with no training, with probability approaching 1, provided that the amount of output noise is not too large. So that's actually rather interesting. It says that in this setting, there is the bells and whistles of GCNs do not actually seem to provide much provable classification benefit. You don't even need to train these things for this problem. Okay. We also have further results that provide concrete examples. So we were able to construct an explicit family of graphons such that every pair of graphons is 0 exceptional, while infinitely many pairs have large cut distance. So in other words, there are a bunch of pairs of graphons in this set that we've constructed that are well separated in terms of the cut distance, but that nonetheless are difficult to distinguish based on their embedding vectors. And these are based on one particular class of stochastic block models. Essentially, you choose some base stochastic block model, and then you perturb the parameters of it in one particular direction, and that generates this class. So the intuition here is that when you perturb the parameters of this base stochastic block model, it preserves the expected vertex degrees while changing densities within and between blocks. Okay. And we have a corollary that says that that gives a probability of error lower bound in distinguishing these two stochastic block models. Okay. So just I want to give a high-level summary of the consequences of our results. Metric convergence of embedding vectors coming from GCNs implies poor performance when you train them, or when you use them to train Lipschitz classifiers, so classifiers with small Lipschitz constant, or with margin-based losses, or that output probabilities. So, for example, if you trained a logistic regression model on on these output embedding vectors, it would not do very well, because all of the embedding vectors are close together, and therefore it should output for any given graph sample from either class some number near 0.5. It should also be noted that a small Lipschitz constant is important in a classifier, is important to give adversarial robustness guarantees. So our results have implications for adversarial robustness. And as we saw, the metric convergence of embedding vectors implies information theoretic indistinguishability of different classes of random graph models in the presence of numerical error from rounding, which is we see numerical error frequently in in practical implementations of neural networks. Okay, so I'm going to talk a little bit more about slightly more recent work. This was published last year. This was single author work, where I wanted to understand the role of the embedding dimension, which is to say the number d, the size of the vector that it outputs. So the concrete question is, what happens to the set of pairs of graphons that are indistinguishable when we vary the embedding dimension? And it turns out that if we the set of indistinguishable graphon pairs actually does not change when we vary the embedding dimension, which is rather surprising. So I've also considered tweaks on this problem to see if how embedding dimension affects other things. So I'll probably skip a lot of this so that we have time for questions. I do have a theorem that gives a multi-class classification error probability lower bound. So here we have k delta separated graphons with a given noise level. And I can lower bound the probability of error. And here the embedding dimension is important. Essentially what this says is if the noise level is at least, this should be theta, omega of 1 over n, not omega of n, then the embedding dimension has to be at least omega of the log of the number of classes in order to distinguish between the classes with high probability. Okay. So just to wrap things up, the main takeaways are as follows. There's really only, in this setting, one statistically hard kind of pair of graphons. Statistically hard meaning that it's hard to distinguish between them based on their samples, based on the embedding vectors of their samples. And these pairs of graphons are the ones that have equal expected degree profiles. And in that case, even if you have nonlinearity in your architecture, it doesn't help. Outside this set of pairs of graphons, so that is to say, if the expected degree profiles are not equal to each other, then the graphons are trivially distinguishable without any training or nonlinearities. So the bells and whistles of GCNs in this application don't seem to be important. Let's see, at least in the 2 graphon case, the embedding dimension seems to have minimal impact on distinguishability. So the conclusion here is that the bells and whistles of GCNs aren't that useful for classification of exchangeable random graphs without vertex data. I should say that I don't, it's important not to let's say overstate these results. There are numerous open problems here. And so I think in future work, it's important to gain a clearer understanding of for which problems are graph convolutional networks useful. So as I was saying, there are lots of open problems. So one of the most important things is, does anything change when we ask the same question for sparse or colorful or small graphs? So implicitly, exchangeable random graph models are necessarily dense unless you normalize them. And so it's important to extend our results to sparse random graph models for which graphons are inappropriate. Furthermore, our results are asymptotic as the size of the sample graph tends to infinity, whereas in many classification tasks, the sample graphs are small. For example, in chemical classification, you're dealing with chemical structures that have maybe, they could easily have at most 20 vertices. So you can't, so to get a full picture of how GCNs work and what their benefits are, we need to study small graph sizes. We can ask various other questions that are listed on this slide. But now I'm going to open it up to questions.
Okay, guys, go ahead and ask Abram questions. So Abram, let me start.
Okay.
So you started with a nice chemical example that actually I think was very interesting.
Okay.
Did you apply it to real data and how it works?
Yeah. I applied it to, we applied it to real data. It's actually published in, I think, Oxford Bioinformatics. So our results applied, so we applied graph convolutional network architecture on this chemical classification problem, and it achieved state-of-the-art results. So these things actually do work in practice. So note that let's see, in that setting, the molecules that we're dealing with really are quite small. They're like sometimes, as I said, 20 vertices. So each vertex corresponds to an atom. Furthermore, it was a multi-class classification problem with node features. So there are lots of the practical uses of these architectures are substantially more complicated, I would say, than our theoretical results at this point.
It's usually in practice.
Yeah,
okay, let me go back, Abram, to the question that I started. So if I understand your model, let's assume I have a sequence of graphs generated by a model. So it's more hypothesis classes. Can you apply this and to tell me which model generates from a set of models?
Yeah. So that's the multi-class classification problem. So if I understand you correctly, if you have a finite set of models, that would be a multi-class classification problem. So each model is a class.
Preferential attachment duplication model, Erdos-Renier, let's say the block model, and you have a, let's say, sequence of generation of graphs, and you decide, yeah, the model that generated is most likely coming from this. You can do it?
Yes, yeah. That's kind of the question that we asked. The key here is you want a rich enough class of models to make it very interesting. And the class of models that we dealt with were Graphons, right? That's an uncountably infinite class of models. Instead of just listing discrete models, so we prefer to have a large class of models.
I'm not sure I understand this one. So comparing to what you're starting, this chemistry, you identify the structure of a chemical bond based on distributions, based. Okay.
Sorry. So the goal there is to so these different compounds belong to different classes. So this compound, let's say, is a carbohydrate or not. Maybe it's a protein or something.
But how you decide it? Based on structure or distribution?
So based on structure, and you learn this from input data, from labeled input data.
Okay.
That's structure, important.
Not based on the models then generated, correct?
Well, you're learning from these. Implicitly, there are models, right?
Okay.
You can think of as okay. So you can think of carbohydrates as extremely, okay, you can think of the class of carbohydrates as an extremely complicated random graph model whose structure you have no understanding of. And so you try to learn how to tell what is a carbohydrate by looking at different molecules that you know are carbohydrates. So you're learning from data.
So what my understanding is the following. You are assuming, and that's probably true from practical or from theory of chemistry, that every component that generates the structure is generated by a kind of a different model, correct?
Yes, this is it's a mathematical abstraction of the problem. Yes,
and that is close to practice.
It appears to be. Yes.
Okay, good. Okay, guys, more questions?
May I have a question?
Go ahead.
So I wanted to ask about these graphons. So you say it's enough to parameterize like uncountably many families of graphs, but is it like complete in some sense? Like what are the limitations of such classifications? Because like, for example, I think that it cannot be used to classify families that are not random graphs. But apart from that, I don't know.
Right. So graphons, the class of graphons is complete in it's complete in the sense that it completely parameterizes the set of exchangeable random graph models. It cannot generate anything that's not an exchangeable random graph model. So for example, it cannot generate a preferential attachment model. In fact, it cannot generate sparse graphs at all. So there are substantial important limitations to graphons, which by the way, people are still currently working on limit theories for sparse graphs. So this is a very active area of research.
May I ask a question exactly about the sparse graphs? Because, okay, graphons are a great tool, but how would you attack the same problem on sparse graphs?
Okay, so you, let's see. You can do one thing with graphons, which is let's see, you change the graph generation procedure. You, instead of generating an edge with probability W of X comma Y, you generate an edge with probability some normalizing factor times W of X comma Y, and that generates semi-sparse graphs. But what it cannot do is generate, for example, bounded degree graphs. For sparse graphs, there are alternative limit theories. What one is called Graphexes. It's a little bit complicated to define, and I'm at present a bit fuzzy on the details. But if you want to look up, I'll type it in the chat. Sparse graph. So Graphexes are sparse graph limit objects. But so there were various open problems here that I'm not completely up to speed on yet.
Thank you.
Yep.
Any more questions? Okay, we thank Abram. It was great talk. If you want to, if you have more questions or you need more details or you want to talk to Abram, you know how to find him. Thank you, guys. See you next week. I will be talking next week.
Thanks.
Bye-bye.
Thank you.
Bye.
Thank you. Bye.
Bye.